Good morning. We are Group 4201 and this is our presentation for our thesis using an Arduino-based maintenance system for an indoor portable smart planter. The proponents are me, Mr. Anshado Jericho, Ms. Bautista Alisa Reno Nicole, Mr. Paner Stephen, and Mr. Tupas Jedrick Angelo. The goal of home gardening is to remove isolation, remove boredom, be free from stress, and provide education and practice on how to manage our plants. Other commonalities of our IPSP are the Lua Smart Planter, Aero Garden, Click and Grow, and Green Joy. These are very expensive alternatives and are not common at all here in the Philippines. The edge of our IPSP is the IoT it provides, the research data you get from the IoT, and the automation it gives. The study specifically aims to answer these following questions. Firstly, what are the components needed for the indoor portable smart planter to grow plants indoors? Secondly, what variables are controlled in order to provide a stable environment for plants to grow in the IPSP? Thirdly, in comparison to traditional outdoor planting, is the IPSP's capability to grow plants indoor the same or better?
Framework. According to Alauri M. Babalola, 2018, current agricultural practices depend heavily on chemical inputs, such as fertilizers, pesticides, herbicides, etc., which all things being equal cause a damaging effect on the nutritional value of farm product and health of farm workers and consumers. Of course, as consumers of marketplace products that have chemical inputs, we want our food to be safe and free from harmful chemicals. On the other hand, we also want to help our farmers with increasing their crop quality and yield without sacrificing the safety of people. If we are able to create a device that can steadily produce crops that are high quality without the need for chemicals, we can open up a lot of opportunities in our country sectors. Right, the figure shows the conceptual framework of the research, which is the IPSP. For the input, the proponents should be familiar with prototype design and microcontroller units. This is required in order to create a smart planter prototype. The hardware that will be utilized is also included. These hardware materials are required to make the prototype functional. Furthermore, because C++ is the major language that will be utilized by the microprocessor, the proponents should be familiar with it. For the process, the proponents establish the requirements by examining the issue that the environment is experiencing as well as the potential solutions. The proponents also set up the prototype's conceptual design and block diagram. Afterwards, the proponents have laid their schedule of activities on which they will going to follow. It also includes the coding of the prototype and developing of it. The proponents will then go through several testing up until the requirements will be fulfilled. Finally, after undergoing different testing, the study was fulfilled, which is the device that helps its user to maintain their plants.
The significance of this study is to mainly innovate and develop the Indoor Portable Smart Planter, or as we call it, the IPSP. It is an Arduino-based crop maintenance system which promotes recreation, research, food source management, and education. This research paper is expected to be beneficial to the following people. First, this study will help households that do not have any backyard spaces, windows, or spots within the house where sunlight can pass through. This will also be beneficial to people who are interested in starting gardening as a small hobby, but they don't have the time to do so due to their daily responsibilities. This study will also help indoor gardeners who would be interested in such a method of growing plants in spaces where light doesn't have to reach. This study will also help businesses that would like the appeal of growing their own herbs and vegetables for their dishes while showing such a aesthetic and atmosphere within their buildings. This study will also help workplace environments such as schools, universities, or offices that do not have the suitable conditions to grow plants, or doesn't give enough care for the plants to survive well. Lastly, this study will help future researchers that may get an idea and motivate them to conduct a study in line with this. This leads to further improving the IPSP. As the study focuses on innovating and developing the indoor portable smart planter, it will be done by using ESP32. It contains controllers such as an irrigation module, light module, and a temperature module. The IPSP contains a function that allows it to run automatically while being controlled by a microcontroller. The smart planter can only cultivate a limited amount of plants at a time, and the ones that were available to the proponents are lettuce and sweet basil. The proponents will also try to cultivate green onions by regrowing onion bulbs. As for our null hypothesis, the plants that grow using the indoor portable smart planter grow at a similar rate compared to the plants grown outdoors. As for our alternative hypothesis, the plants grow better despite the indoor environment and lack of sunlight, and the chosen smart planter components make up a sustainable maintenance system while making it affordable to recreate and rebuild.
The design used in this research is experimental. We tested how the IPSP can grow plants despite the environment indoors. Divided into two groups, one will rely on the IPSP prototype, wherein experimental factors are taken into account and adjusted for feedback. The second group will rely on a more traditional method of planting outdoors, where they are exposed to a fluctuation of measurements in the environment. Any target and set parameters for the experiment are based off of previous researches. For the data gathering procedure, data from the sensors inside the prototype are remotely transmitted through the IoT system. The data such as temperature and humidity, soil moisture, light hours, and water levels are recorded once per day.
Statistical treatment of data. The gathered data through 10 days of observation of growth of onions will be analyzed to determine the significant difference between traditional planting and using the IPSP. The proponents use the man-Whitney use test and non-parametric test as the statistical treatment in the study. It is a method that allows researchers to compare two independent groups to see whether there is a difference between the two groups. The proponents use a software called SPSS or Statistical Package for Social Sciences version 20 to utilize this test.
The indoor portable smart planter will collect real-time data through the use of the sensors inside the prototype. These sensors will send those output locally to the Arduino ESP32. The microcontroller will then relay these figures to the IoT cloud for monitoring through the IoT dashboards and the Arduino website, or to our local software applications installed in our mobile devices. At the same time, the Arduino ESP32 will use the system to adjust the measurements of these data through the use of the feedback system built in the prototype, such as the fans or the LED lights.
Our schematic diagram is made in Circuit Wizard. Even though Circuit Wizard does not have the ESP32 in its component list, we created nodes in the right side of the circuit in order to simulate the ESP32. On the top left side, we have our 12-volt power source supplying power to the LED strip and the fan, which is then connected to a transistor and then a resistor into the ESP32 pins. On the bottom left of the screen, we have the ultrasonic sensor and our water signal sensor connected to the pins of the ESP32. And at the bottom right of the circuit, we have a soil moisture sensor and our humidity and temperature sensor connected to the 3.3-volt power source of the ESP32 and the pins of it also.
As for our flowchart, which shows how the maintenance system works, it starts from initializing all tasks needed. And as you can see, there are three processes that occurs all at the same time, and I will explain how they work one by one. First, it checks if the current time is 7:30 p.m. If not, then it's still morning, so the LEDs will light up. If it is indeed already 7:30 p.m., then the LEDs will turn off. This is to create an artificial daylight cycle on the planter. Next, it checks if the surrounding temperature is less than 36 degrees Celsius, which is usually room temperature. And if it is, then it prompts the fan to turn off. If it gets hotter, then the fan will turn on to regulate the temperature. Lastly is how data log works. The data from the ESP32 was received from the sensors. Then it stores the data to the Arduino IoT cloud, which made it possible to turn the IPSP into an Internet of Things. After that, it shows the data gathered to the dashboard where the user mainly observes the status of the IPSP. With the compact design of the IPSP, there is no way to see how much water is left. So the sensor within it will indicate the water level for the user. So if it is already less than 50%, then it will prompt the user to refill and it will show the water level on the dashboard. And if not, it will simply store the data back and display it on the dashboard.
Results and discussion. So, in our experiment, we have 6 onions planted indoor or two using our IPSP and 3 onions planted outdoor. In the left table is a result of the Mann-Whitney U-test using software called SPSS. And it was used to compare the differences between indoor and outdoor planting methods. Based on this table, the test found no significant difference between the two dependent groups, IPSP and conventional planting. Since the p-value, you can see in exact significance, is 0.548, it is greater than 0.05 our confidence level. Hence, the null hypothesis is not rejected, so there is no significant difference between the two methods. In the right table is the average of temperature, humidity, and soil moisture of indoor and outdoor in 10 days observation of growth of onions. You can see that there is little differences in the data from indoor and outdoor groups, which interpreted that the environment indoors is technically the same as the outdoor plant environment, only without natural sunlight and rains.
Our summary of findings showed that firstly, planting has become a staple to many households not only in the rural areas but in the urban cities as well. People in the cities, however, have a much more difficult time taking care of their plants unlike in the provinces due to how small the spaces in their own home can be. The hustling culture in the cities can also mean that people won't be able to spend extra time taking care of their plants. Secondly, using related studies, the proponents collected necessary information to create a general idea of which components will be needed. Afterwards, the design phase was done using 3D rendering simulations. The design phase went through multiple iterations until the final design was approved unanimously. Every component was first tested before the prototyping of the IPSP was done. After experimentation on plants, the components are calibrated one by one until the prototype works satisfactorily. Thirdly, the proponents conducted 3 beta tests to prove that the IPSP can grow plants and compare them to traditional planting. For the first 2 beta tests, basil and lettuce seeds sprouted but died afterward, the same as in outdoor plants. Thus, we concluded that the seeds are defective. In the last beta testing, the proponents used onions to get data for the study. For the 10 days of observation of onions planted indoors and outdoors, they showed growth. The researchers measured it per day. Using the data gathered from the growth of 6 indoor onions and the 3 onions outdoors, researchers applied the Mann-Whitney U-test to compare if there are statistically significant differences between the two methods of planting. The proponents found that there were almost no significant differences between the two.
It was therefore concluded that the proponents were able to create a prototype that produced satisfactory results. With the help of previous research gathered, the proponents were able to compile the much needed components into a single prototype that can sufficiently sustain an environment for plants. The proponents also observed some similarities in temperature and humidity data from indoor and outdoor groups, which interpreted that the environment indoors is technically the same as the outdoor plant environment, only without the natural sunlight and rains. Although the water container of the IPSP was constantly refilled during the course of its testing, the proponents conclude that the IPSP can be left behind on its own for about 7 days straight without refills.
Finally, the proponents would like to recommend the following to the future researchers who would undertake a similar study to ours. First, the proponents highly recommend improving on the build of the prototype itself. Instead of wood, other materials such as plastic or acrylic would work much better in terms of durability and weight. Imprinting the system to the build would also achieve a cleaner look. Second, the proponents recommend maximizing the capabilities of the Arduino IoT. The proponents are very limited with the software that is utilized. In doing so, more specific controls can be done and more factors can be changed by the system itself. Making the system also independent should allow it to run indefinitely regardless of power and internet outage. Last, the proponents recommend experimenting on multiple plants to fully test the system's limits, as well as extending the experimentation time from seed to fully grown harvest.
The following slides contains the complete list of references gathered and used for this study's review of literature. This will also conclude our presentation and will move towards the hardware and software demonstration of the Indoor Portable Smart Planter or IPSP. Thank you very much for listening.
Thank you very much for listening to our presentation on our thesis using an Arduino based maintenance system for an indoor portable smart planter.